Right, this is a walkthrough for CSM 61C week 9 for virtual memory. So in general, virtual memory on a high level is just mapping your process memory, your physical memory. And this avoids fragmentation. So you have all this memory in a contiguous block in this way, and it maps to physical memory, which may not be contiguous or may be in different locations. And overall, it can give us the illusion of more memory than what we have, because for each process, you basically have another set of virtual memory, and then you can have the illusion of more memory than is physically given by paging and basically by switching between memory between like your processes. So then you can map to like many different locations and look at different locations of memory. You can look at your main memory in like the RAM and the secondary storage in the disk as well. And so for this week, we're gonna be covering like the translation of memory addresses to physical addresses. So the main use of our virtual memory is to map like our addresses and be able to translate our addresses so that when a computer gets some address, it knows where to look at for physical memory and like what that address corresponds to in your code. So for this warm up, so a system in question has 1 megabyte of physical memory, 32-bit virtual addresses, and 256 physical pages. If we have a fully associative TALB and with 128 entries and a least recently used replacement scheme, which is when, excuse me, when we basically evict a page when we evict a page from memory, like when we have a page fault, we replace the page in like our cache with the one that was used the furthest, or the least recently used. So you basically throw out the page of your memory that was used furthest away, like chronologically. So knowing that, the size of our physical page can be determined from our data given here. So 1 megabyte is 2 to the 20th bytes of physical memory. And then we have 256 pages. So which means we have 2 to the 8th amount of pages. So our size of our physical pages can just be, it's just calculated by our physical memory divided by our page size, or the number of pages we have, and that gets our page size, which is 2 to the 12th, which is 4 KB bytes. And then virtual pages should be the same as the physical pages, since all pages are the same size in the same system. So it's just 4 KB bytes again. And in terms of maximum number in the virtual page, so we have a 32-bit virtual address, which means a 2 to 32 bytes virtual memory, right? So using that and using the page size that we calculated, we know that we have 2 to 20 total virtual pages. And the minimum number of bits required for the page table base address register. So the page table is also stored in memory. So the page table base address register, its address is the same amount as the other addresses that we use. So it spans a physical address, and we know that our physical address is we have 2 to 20th total virtual pages. So then we have our virtual memory, and then that gives us our bits. So like when we have a certain size of memory, it corresponds with log 2 of that. It corresponds to how many bits represents that. All right. So the system in question has 1 megabyte of physical memory, and 32-bit virtual address. So same as last time. So is the page table stored in main memory? Yeah, because the page table requires accessing the main memory. I guess that's more of a conceptual, factual thing. Each virtual page is mapped to a physical page. So that's false. So only virtual pages that are being used are mapped to a physical page. by the page table. So we could, in like our whole virtual page, this is kind of a trick question, but because we would never like use something, we would never like access it because it's unused. But if we're not using every single virtual page allocated to us, then it's technically not mapped. So TLB check before page table. So the TLB is a cache to the page table. So the TLB basically speeds up our address translation because it directly maps our one address to another. So like when we translate like a virtual address to a physical address, we just look at if it's present in the TLB, and if not, we would pull it from main memory. So yeah, so we would always check that before. It doesn't make sense to check it after. So the penalty for a page fault is about the same penalty for a cache miss. So this again is a little bit more factual, but our cache miss means that we pull our data from main memory. And if we have a page fault, that means it's missing in memory. So we need to pull it from our disk, our secondary memory. And that will take longer, which kind of makes sense because like the hardware, it's our secondary memory. So it's essentially our backup. So we design our memory to be accessed faster. So that may be a good way to think about it. So linear page table taking up more memory as a process uses memory. So it takes the same amount to store the entire page table. So like, I guess this one doesn't, I'm not sure exactly why this one's there. I don't know if it makes too much sense, but as as we keep on storing, it takes the same amount of memory. I hope that like conceptually is intuitive. Okay. So with these assumptions, with our 16-bit virtual address, 4 KB page size, 16 KB virtual memory, LRU page replacement, and fully associative TLB with 4 entries, and again, LRU replacement. So what's the maximum number of virtual pages per process? So for this one, we need to get our maximum number of virtual pages. We're given our 16-bit virtual address. So what we can do is our number of virtual pages is the number of 2 to the power of the number of bits in our for our virtual page number, because our offset is like kind of our identifier. The virtual page numbers represent like an identifier for each different page. It represents basically like a hash key for each different page. So we have our 16-bit virtual address, so it's going to be something less than 2 to 16th. And we have our 4 KB page size, which is 4 KB is 2 to 12. So I think I put everything on there. That's okay. So 4 KB is 2 to the 12. So it's 12. We have 12 offset bits. And from 16, we have 4 bits for a VPN. So then with that, we have 16 different options for pages. So at max, we can represent 16. It obviously can be less. And how many bits wide is our page table base register? So our page table base register is, again, in memory, kind of from the last question, along the same lines. So it's the same length as a physical address. So 16 KB is 2 to the 14th bytes, so 14 bits wide there. Yeah, so 2.2. Right. So in this one, we're given this code block, and we're assuming only this in memory. We're assuming everything's page aligned. The arrays are the same size, do not overlap, and all the code fits in a single page, and it's the only process running. And of course, with these, the assumptions from previous, which are listed here. So if scale and copy were called on an array with n entries, where n is a multiple of the page size, how many page faults can occur in the worst case scenario? So our worst case is, again, if our TLB is empty, right? Because our TLB allows for fast address translation the first time. So if it's empty, then it's always going to result in a page fault. So our page fault on our first access will always happen because it will never be in the TLB. So how many integers per page? So we have a 2 to the 12 bytes page, which is based on our offset from last time. And we have our 2 to 12 byte page. Our integers are 4 bytes. So we can store 2 to the 10th integers per page. which is quite a lot. So how many accesses per iteration? So if we look at our code, we have an access here. We're writing to copy I and we're reading some element of base. So we have 2 accesses per iterations, the number of iterations we do in this for loop. So our total accesses, we have 2 times n over 2 to the n, right? We have n entries, 2 to 10 integers per page, and then we do that twice. So we have 2 times n over 2 to the 10th pages access, which you can also write as 2 over n over 2 to the 9th. And then is the code already in TLB? So because our code itself, like our code isn't in the TLB, or it's going to be +1. So that's just one thing to remember on like an exam or anything. It wouldn't be just the exact number of accesses. You also have to determine if your code is in the TLB already. And sometimes they'll say that it is in the TLB. So you just have to keep track of whether it is or whether that is in your assumptions or not. Okay. So now best case in the scenario, how many iterations of the loop can occur before a TLB miss? So we have 4 TLB entries as given in our assumptions. So if we assume like one of them is for the code, we have 3 pages in the TLB to use. We have 3 pages in the TLB that we can store in the TLB. So yeah, so we basically, our TLB is populated with our desired pages. So we have code, we have the code, then we have the base, then we have copy. So with 2 to the 10 integers per page, we can do 2 to the 10 iterations before we have a miss. So a page is 2 to 12 bytes with 2 to the 10 integers. And because we use these 3 pages here, we can store all of our, I guess we can store, or not store, but have that stored in the best case, have 2 to the 10th integers in the best case to be present in our TLB before like we have to miss by like the pigeonhole principle and all. Yeah, hope that made sense. I know those questions aren't super intuitive, but most of them are just doing math given your assumptions and just thinking about like what best case and worst case scenarios are. Those are pretty common problems. So yeah, so let's think of, so we're given these assumptions now. So again, we have a fully associative TLB, and that's usually what a TLB will be. It's designed to be fully associative. So it wouldn't make too much sense if they give you a question without it being fully associative, because that's like what's designed on computers. But anyways, so we have a fully associative TLB with 2 entries with LRU replacement policy. It's initially cold, so we don't have any, we're not going to encounter any hits like the first accesses. We have 2 11 bytes of virtual memory. We have a 10-bit physical address space and 256 byte page size. So in terms of how many bits are in the VPN and PPN, so we have a 256 byte page size, which means we have 2 to 8 byte. This should be 2 to the 8th. Sorry about that. But 256 is 2 to the 8th. So we have an 8-bit offset. Remember, their VPN and PPN offset will be the same because the page sizes are going to be the same. So we're given our 10-bit of physical address space. So our PPN has a 2-bit because it has an 8-bit offset, of course. And we have 2 to 11 bytes of virtual memory. So which means we have a 11-byte virtual address space, or 11-bit virtual address space. Offset is 8 bits, so 3 bits of virtual page number. So how many entries should a single level page table have? So remember, a single level is just where we don't have we don't continually map. So we only map it once. Like our virtual page numbers just map to like some entry there. So it just corresponds to how many total like virtual page numbers a page table can like correspond to. And since our virtual page number is 3 bits, it can have 8 different entries. So a single level page table is like when we have some address space, right? We have some address space. adder, like it can correspond to like some number of entries, right? So that's like a single level page table. And a double level page table will have these ones also have some entries here. And that's to like handle sparse address spaces and stuff like that. I'm not gonna draw this whole thing out, but that's what I mean. I think it's a little bit easier when you draw it out. And I'm not sure if my explanation made much sense, but yeah. So final question, how many pages are in physical memory? So again, that just corresponds to how many bits you have for a physical page number, because your page number can only correspond to so much. So it's just 2 to the second based on the number of bits in the PPN. So 4 entries there. So clear my drawing. Right. So this one kind of walks through like a certain amount of memory accesses. So I'm only going to do probably the first 3 or 4 and then just show the rest, and hopefully you can do them on your own, because or else like it would take way too long. But basically we're just mapping a certain address to its virtual page, to its page number and offset and stuff like that. And then we're checking if it's in the TLB, and if it's not, then we look at the page table, and then we use LRU page replacement. And we're given the same assumptions as we were before. So I think we're checking, I think this is assuming a cold TLB. So a good way to map this is like a very formal way to map it. In reality, you just have to keep track. If you can keep track in whatever way is more convenient to you. Like this isn't like a hard and fast way to do it, but whatever makes sense. But I think it's pretty useful. So let me look at this. Okay. So in this one, we want to separate our virtual address and our offset. So if we write this in binary, then our virtual address, our VPN, remember, is our first 3 bits, and our offset is the rest. So we don't really need our offset when we do the TLB page number in physical memory. That's just more about identifying the actual memory address. This one's, we just need to know like which page it corresponds to. So, right. So the typical algorithm will be, if our VPN's in the TLB, then we can just get the PPN directly. If not, we just look at the page table. If so, then we get the PPN direct from there, and then update the TLB to reflect, because it's least recently used. So we want to put that in our TLB. We want to put that in our cache. And then if it's not in the page table, then we want to basically get it from our memory, and then update on every access. Yeah. So our first one is our memory access is 1, 2, 3. So there's nothing in our TLB or page table. So it's going to be a TLB miss and a page fault. So then we basically would just want to grab our data from our memory. So yeah, and then we populate our TLB and page table so that we have hits. So our VPN is 1. Our PPN is 0. Yeah, because of our PPN is our given bits as described from last time. So again, now we're looking at 4, 5, 6 in hex. Again, it's not there, right? Like our VPN is 4, or yeah, 4. So there's it's clearly not in our TLB page table, which is very empty at this point. So then we have to fill in our memory and populate our caches. So our TLB is full, but it would have been a miss anyways. Our page table doesn't have our VPN in there, our VPN of 7. So then we grab our data from our memory. We have 2 misses again. And our TLB is full now. So because it's full, we kick out the least recently used. So in this case, it kind of color codes the values to make it easier, but our least recently used here is clearly the 1, 2, 3 from the first one, in case that didn't make sense. So finally we have our first hit, our first TLB hit, because we use 400, right? So our virtual page number 4 was in our TLB. So we just grab our PPN from there, and then we update our caches as such. And there's no need for it to be in page table. And here 3213 is a miss on both TLB and page table. And then yeah, we basically grab our memory, and again, it's least recently used. So yeah, I hope that kind of describes a pattern. This is like I could see this being an exam question just to make sure you know like the replacement policies. It's more about that. It's more about the replacement policy and seeing if you know like which bits correspond and how to like read like a memory address and a virtual like address to see, you know, which one's the VPN and which one's the offset, and if you can calculate that correctly and stuff like that. So I think this is a pretty good overall problem. So if you have a little bit of trouble with this, I would, you know, ask a question or try to get more practice on this type of stuff. But I'm just going to show the answers. I'm not going to walk through the rest because this is fairly repetitive. But this is how it turned out. This was the final answer here. So yeah. So our hit rate from our TLB will end up being 3 out of 10, I believe. Yeah, 3 out of 10. Our page table was 1 out of 7. So we have 6 page faults, which is, and it's not great, but with such a small, like, I guess sample size, it's going to happen. So our average memory access time again is when we have it for multiple, you kind of like compound the formula. So with a TLB and like a page table, so we can use our hit time for a TLB, then our miss rate times our hit time from our memory, our miss rate from memory times the miss penalty for the page fault. So we kind of compound the equation to use like our different caches basically. And then that comes from the givens. This equation fills out to be this, which turns out to be 686 nanoseconds, which isn't not too bad. That's pretty fast. Okay, and this one's a pretty interesting problem because it deals with context switches. So a context switch is when we switch processes, and switching process is just basically switching code, switching like what your code does. So when we switch code, our code typically doesn't really remember what we've cached. So it can slow down our computation if we do too much because of all the overhead and not being able to remember that. So for an actual problem, so we're analyzing some virtual memory system. We have a single core computer with 4 KB pages, 1 MB virtual address space, and 1 GB physical address space. The computer has a single TLB that can store 4 entries. You may assume that TLB is fully associative with an LRU replacement policy, and each TLB entry is like of this form, so some valid bit, and then all of this. So given a virtual address, how many bits are used for a virtual page number? So again, this is kind of what we've been doing. We just look at our sizes. We look at any of the hints we have. So I guess I'll walk through. So 1 MB of virtual address, again, is 2 to 20 bytes. We have 4 KB page size, which is 2 to 12 bytes. So then our offset is the log 2 of the page size. So then that's 12 bytes. Our VPN is just our total address size minus our offset, 8 bits. Same story for B, except our physical address size is 2 to 30th bytes. Offset's going to be the same, and our page size is going to be the same. So offset and page size are going to be the same. So our PPN here is 18 bits. So yeah. So now we're actually dealing with the aforementioned context switch. So we're going to run these 2 different processes. So we have this process 0 and process 1. I'm going to put my camera here. So we have these different processes. And when we run them, we have these page aligned addresses. Our computer has only a single processor, so we share times on the PCU. And yeah, I think that's all we need for this one. Yeah, so for A, what's the TLB hit rate for executing the above code, assuming the TLB starts out cold, and only consider accesses to data, and between context switches, we have to flush the TLB. So basically what we need to know here to solve this problem is what will result in a hit after the first one. So we just have to remember that our page size, our calculation that we made here, how that corresponds to accessing these arrays. So when we actually walk through it, we look through like, are all memory accesses within one iteration of a for loop, and are they all in one page? Because if so, then we can just, they're always, it never results in page fault in like one iteration. So you have a 2 to the 12 byte page, and in the iteration we make, in both these iterations we make, this one is clearly a so because it's within, it's all within like these, it's all within 5 integers basically, all within 4. And for this one here, for process 0, all of these are within a 2 to the 8th integer chunk, and there's 2 to 10 bytes per iteration. So we clearly have enough. Yeah, because we have a 2 to 12 byte page, and then we flush when there's a context switch occurs, because we don't save our TLB between processes in this case. So as we walk through it, our first one's clearly gonna be a miss, a cold miss, compulsory miss, and our next one's gonna be a hit because it's in our page. Now as we switch process, we have to flush. So our first access is gonna be a miss, and the next one's gonna be a hit, and then we do the same thing again, right? Like, so our first one's gonna be a miss again because we don't save our TLB. Next one's gonna be a hit, we flush again, miss hit. So it follows that miss hit pattern. So then from there, we know our hit rate is 50%. Great. So now we're dealing with basically a different TLB architecture. So now we're using a tagged TLB. So in a tagged TLB, each entry additionally contains like an address space ID, which uniquely identifies the virtual address space. So basically what this does is we don't really need to flush because it like pseudo like remembers the process that we're in. So it keeps entries in the TLB even if they're not part of the process. Yeah, so that's pretty cool. So for this one, like we don't have to forget our old TLB values like when we switch different processes. So let's walk through it. Yeah, same procedure here. So our first one is a miss, of course, and our next one is a hit. Now we switch processes, but we don't have to flush our TLB. So we have a hit here, we have a hit, we have a hit, we have a hit. So our only miss is when we switch processes and we go through a different loop. Yeah, so that's pretty cool. That's a cool way to save your values, stuff like that. So we have a 75%, we have 75% hit rate for here. We have 3 misses per 4 iterations. And what's the hit rate for the tag TLB? Assuming it again starts out cold. Yeah, so my recording accidentally switched off. Oops. Okay. So for this one, it's more of like what happens in total. So all the memory accesses are again within one for loop, right? We have 2 to 12 byte page, and there's 2 to the 10th bytes per iteration because again, they're in a 2 to the like 8th integer chunk, and an integer is 2 to the 2, so it's 2 to 10 bytes. We have 4 iterations per page of data, and we have them for both of them. So we have 16 like memory accesses per page. And yeah, and we'll like always cold miss on the first one. So we have a 15 out of 16 hit rate. And then what's the smallest number of TLB of the entries in the TLB the TLB can have to still have the hit rate found in the previous part? I'm sorry for this typo. Need to proofread better. So yeah. So in this case, it's 2 entries. So we need to maintain at least 1 page for A and B. So then, because like when it doesn't, basically this just comes from not flushing it. So because we don't need, since we don't like need to flush our TLB, like, and we're only accessing 2 different arrays, having more entries doesn't really matter because like our page size is still limited to like our chunk. So all we can do to like increase the hit rate is to basically increase our page size. So creating new entries in TLB won't really matter because we're accessing the same data. I think that's it. Yeah. So I hope that helped. I'm sorry this is coming out a little bit late because the worksheet did come out a little bit late due to the Veterans Day. But I hope we can get back on track next week. And yeah, I hope you enjoyed your day off. Thank you.